So we have to find the MGF, moment generating function, of this s square variable. So we are aware that n minus 1 s square over sigma square follows chi square n minus 1. Out here our s square is sample variance, sigma square is our population variance, and n minus 1 is our degree of freedom. We are all we also know that chi square n minus 1 is equivalent in distribution to gamma distribution, with shape as n minus 1 over 2 and scale shape as n minus 1, this degree of freedom, divided by 2, and scale equal to 1 by 2. If y follows our gamma distribution alpha comma lambda, this is a dummy variable. This is to inform you of the formula. If y follows gamma, shape parameter equal to lambda, and scale parameter shape parameter equal to alpha, and scale parameter equal to lambda, our moment generating function, our my of t, will be lambda over lambda minus c whole to the power alpha. So by same logic, I have assumed this variable to be t. Our mt of t will be scale parameter over scale parameter minus t whole to the power shape parameter. So I'll substitute the value for t, n minus 1 s square over sigma square of t. So this will be 1 over 1 minus 2t to the power n minus 1 by 2, and when I'll inverse it, it will become minus n minus 1 over 2. So this is another formula. I'll provide the proof for this later in the video. But from here we can understand that this a is equal to n minus 1 sigma square, because in this formula we have to derive the MGF of this variable using this variable. This is similar to deriving the MGF of this variable using this variable. So from this formula we can see that our main focus is s square. So from this formula, a is equal to n minus 1 over sigma square, and as you can see, there is no additional component. Our b will be equal to 0. So using this formula, m of n minus 1 s square over sigma square of t, this will be e to the power bt b0 mx of there's no x, m of s square of n minus 1 over sigma square, our a here, into t. So this we already know, it is 1 minus 2t to the power minus n minus 1 by 2, e to the power 0 t is 1, m of s square n minus 1 over sigma square into t is this. So now I have to substitute a t as such. This I can get only one variable. For example, this I can get only small a, and this will be modified according to that. So I want n minus 1 sigma square into t. I want this to be a single variable, so I'll use it as a. By this logic, my t will be equal to a sigma square over n minus 1. So can I use this? Let's try. So m of s square, I've already assumed all of this to be a, so that's good, and this t will be a sigma square over n minus 1. So 1 minus 2 a sigma square over n minus 1 whole to the power n minus 1 by 2. So it turns out I have evaluated m of s square of a. Okay, now I can substitute this back into t. This a was just a dummy variable. This was just a dummy variable. M of s square of t, this will be 1 minus 2t sigma square over n minus 1 whole to the power minus n minus 1 by 2. And let's check if it matches. 1 minus 2t sigma square by n minus 1 whole to the power minus n minus 1. Yes, matches perfectly. So now to provide the proof for this formula, what is our mx of t moment generating function? It is equivalent to e to the power xt. We are clear on this. So what will be our moment generating function of this? E to the power ax plus b into t. So this looks like it will be axt plus bt. Now this bt is our constant, b is a constant, t is a constant, there is no variable in this x, so we can bring it out by property of expectation. E to the power bt, e to the power axt, axt. So now as you can see, I have gotten this in the same format as this one, e to the power xt, e to the power x into some constant. So I can substitute it again in this format. I can substitute it again this in this format. So this will be formatted into e to the power bt. We have already got mx of at. So this is the short proof of this, and we have gotten the answer. Thank you.